In this video module, we'll be discussing using or developing models in R. And the module is based on an example from chapter 23 of our textbook, the R for Data Science textbook, and you can see the link here right here. And I also assume that you've already read chapter 22. The link is here for that chapter. If not, you should definitely stop the video and go back and read it. It's a relatively short chapter, and it's important for the material that we're going to cover. So our objectives in this module are twofold. First, we're going to define and discuss the concepts of a model family and then model instances with respect to a particular example. I will make a note, this is a different example than is done in chapter 23. And so while we follow the same structure, we're using a totally different data set. And so this is something you want to have a look at in that chapter also. And then secondly, we'll illustrate a simple search-based procedure for selecting a good model from the set of models that, that we generate. Okay, so let's have a look. Let's jump over into our studio, and the script file that I'll be using is models example 1, and so this will be available in the video module. It's also available in the course repository. And so we will, as usual, load tidyverse. We're also going to load a package called Model R, and we'll come back and talk about what that is towards the end of the module. And we have a simple data set, and it's in this file regsample.csv. So let's read that in, and then we can look at that data set. So just go here and say df, that's our data file. And so this is simply a data frame that has 25 rows of XY data. And so what this actually is 25 random observations from our real estate data set, where X is the square footage and Y is the price of the house. And so this is just a sample data set that we can use to discuss the problem. Our objective is to take our data frame and develop or create or find a model that explains the relationship between y and x, between the two variables y and x. In our case, we know what this data is. X is the square footage and y is the price. So we want to identify a model that explains that relationship between the price of a property and the square footage. So of course, the first thing we're going to do is just take a look at the data. So I have a plot here. We're going to just do a scatter plot. And there is the plot of our data. So you can see we have 25 data points there. So I'm going to jump over here into OneNote so that I can draw. This is simply the plot that we have there. And so in creating this model, let me just grab a different color here. There we go. The first thing that might jump out at you is it looks like there's a linear relationship. And so we can assume that we have, or we can suppose that we have some model that might look like that. Let me get a smaller pen here to talk about that. There we go. And so the question is, what is that model? So what is it that we want to try to develop? And so I'm sure some of you are thinking, those of you who've had statistics in particular are thinking that we're talking about linear regression. And I'm going to talk about this sort of in a more general form before we jump into the standard linear regression. And so what we're going to do is we're going to develop a model that says, let's suppose we have y equals some w1 parameter plus w2 times x plus some error term epsilon. So in our terminology, this is what we would call a model family. Model family. It's a model family because we have a parameterized set of data. We have w1 and w2 are the two parameters, where w2 is what we think of as the slope and w1 is the intercept. And to take the model family and create an instance, or to observe an instance from our model family, we need to assign values to our two parameters. So for example, let's say let w1 equals 0 and w2 equals 150. And so this gives us a model. Y hat is equal to 0 plus 150x. And so this is a model instance, or generally just a model. and this model belongs to our model family. Let's go back to our R script and we can implement that model, which I have here in my code. So there's, let's see, control enter for W1, W1, W2, and then we'll plot that. So we plot those values, and you can now see my plotted data points with my model. So this is a model instance that belongs to the model family of a standard slope-intercept line. Now note that this is only one instance, and I can actually create an infinite. So this is one of an infinite number of models. And so next, let's create some random models. And so what this code does is it generates 200 random instances. And so you can see that what I did was I said I want to create a tibble that has two variables, W1 and W2, where I'm sampling a uniform random variate between which is 500,000 and 500,000 for our intercept, and minus 100 and 250 for our slope term. So if we run that, and now we look at our models, again, scroll up here, let's look at models. And so now we have W1 and W2 columns and 200 observations. And so in our terminology, each one of these represents a model. Each one represents a model instance that belongs to our model family. So as we did with the single version, let's plot these. So what I have here from the textbook is the code that will plot all of these. So I give it the data. The data frame is models, the intercept and the slope W1 and W2, and then I'm simply going to plot those and overlay our data points. So when I run, you can see here are our 200 models. You can see each one of them. We grade them out a little bit so they wouldn't overwhelm the plot. And you can see some of these plots are good and some of these plots are bad. So one of the questions that we'd like to answer is, suppose that I find the best one of these models. We're going to talk about how to do that in just a second. But suppose that I have the best one of the models. What does that tell me about the overall quality? So let's assume, for example, that I find the best of these 200 models and call that WB for W best. What do we know about the quality of WB? While it might be the best of these 200, we really might not know much about its relative quality, especially with respect to the overall problem of the actual relationship between y and x, because we don't know that relationship. Even if we have the optimal W, so if we use an analytical solution to find the optimal straight line fit, we still don't know the relative quality of that with respect to the true relationship, and we never really will because we don't know that true relationship. And so the objective here, from a quote from the book, basically the goal of the model is not to uncover the truth, in other words the true relationship here, but to uncover an approximation that's still useful. And of course this quote is from a variant of the famous George Box quote that says all models are wrong but some are useful. And so that's really what we're after, is we're not so much interested in finding truth because that's impossible, but we want to find a model that will be useful that will shed light on this general relationship between y and x. So let's summarize where we are. Let me jump back over into my OneNote. Let's see right here. And so what we've done is we have a set of data. So this is our data frame, x and y, and we have x1, y1, x2, y2, dot, 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 x, let's say n, yn. This is our data. And we have a set of models. Models, w1, w2, so we have w11, w21, w12, w22, down, and we have some number m. So w1m, w2m, where each one of these rows represents an instance of our model family. In part 2 of the video module, what we're going to do is show how we can take this set of models and try to identify a good model and hopefully the best model from this set.